Mm. Okay, everyone. So welcome to Lecture 8 of ECE 3311 Principles of Communication Systems. Let me first turn the audio down here. Okay, perfect. So, so today's lecture, what we're going to be talking about is intersymbol interference. So up until this point in this lecture, what we've been doing is focusing on ideal waveforms. We just finished up eye diagrams. We looked at line codes. We looked at PAM and PCM waveforms. So we have a good feeling of how information is converted from the binary domain into the analog domain using electromagnetic energies and the representation of amplitude levels. But what I want to do here in this lecture is I want to jump into sort of the non-ideal aspects of the communications world. So for that, okay, what we're going to do is we're going to jump into this thing called intersymbol interference. All right. And this is going to sort of set up everything for Lecture 9, which deals with the all-important concept of Nyquist pulse shapes, of which there are a couple. There are a few others. But in particular, we're going to look at something called the raised cosine pulse. Again, that's in Lecture 9. So what we're going to look at right now is the concept of intersymbol interference. Right? So let's get started. So up until now, all we've been talking about is really great ideal world in terms of what we've been communicating over let's say, a piece of copper wire or a fiber optic cable or something of that nature. So let me actually illustrate. So let's go over here. So up until now, all we've been doing is things like this, right? So over time, every TS seconds, right? 0, TS, 2TS, 3TS, 4TS, 5TS. You get the picture, right? And suppose we have some sort of polar non-return to zero transmission where we have, let's say, 1, 0, 0, 1, 1, 0, 1, right? And those are defined as, if it's a 1, it's positive A amplitude, and if it's a 0, it's negative A, right? We have something that looks like this. Okay, fantastic. And the way this would look like is we would have our binary source, bin source, right? Shorthand. It goes into this mapping function for polar non-return to 0. It then goes across some sort of communication medium. And then what it will do is then we do the conversion, the mapping back to binary. And then we have bin sync. Fantastic. And this thing, until now, we've been assuming ideal, right? So ideal means that if I transmit this thing, this collection of polar non-return to 0 waveforms, here, I'm going to get the identical thing out here. and it's going to go back into the mapping, and everything will be perfect, and we'll all be happy, right? Well, that's the reason why we're taking this course, because this is not an ideal world, right? So what ends up happening is, so far we've been looking at rectangular pulses. Except for class test 2, I decided to go a little bit more crazy and chose triangular pulses, mainly to sort of say, okay, well, we have these rectangular ones, and then triangular is actually the convolution of two rectangular, right? But in general, rectangular pulse shapes are not super cool, right? Why is that? Well, rectangular pulses are not cool because of this. So we look at the time frequency relationship between the two, right? A rectangular pulse and its Fourier transform equivalent, okay, pi f TS, correct? Okay, so what does that look like? Well, this we know in the time domain, it's going to look like this: 0, unity, minus TS over 2, TS over 2. And this here, folks, is going to look like our friend, the sync pulse, right? 0, 1 over TS minus, sorry. And that's going to be 1 over TS. That's going to be 2 over TS, and all the zero crossings minus 2 over TS. Fantastic, right? And then there is that. But there's a problem. This. You might say, well, what's the problem? It has zero crossings. Yeah, but the problem is it's not spectrally contained. Because what ends up happening with these sync pulses is that they go all the way to minus infinity and all the way to plus infinity. So if I'm looking for something, this is a very important term. You're going to hear this a lot in the communications world. Band limited, right? This is anything but band limited. So band limited means that it doesn't stretch to minus infinity infinity. Because, for instance, in a communication system, suppose here's in the frequency domain, you got to coexist with a whole bunch of other transmissions. Unless you have your own dedicated medium, in which case, completely different story. But that's pretty nice, but doesn't happen all the time, right? So let's say that's you. That's you, right? But this is someone else. And then over here is someone else's friend. So the problem here is that if you have your sync pulse, you don't stop in your spectrum. You keep on going into your into someone else's and their friends and stuff, all the way to minus infinity to plus infinity. It's not, and if they do the exact same thing, they interfere with you. Now, sure, there's these things like the zero crossings, but that requires coordination with someone else and their friend, right? So if they don't have the same sort of period, right, symbol period as you do, you're in trouble, right? Because now they are actively interfering with you. So rectangular pulse is not super duper cool. Okay. So that's the problem with these rectangular pulses. And in the time domain, like time domain, great. You can see it, awesome, looks great. It's the frequency domain that causes quite a bit of problem. Now, that's the first thing. The second thing that I want to bring up is that diagram I showed before. Let's go back. So I'm just going to generalize all the machinery in the transmitter as TX, and all the machinery, including the binary sync. So sources in TX and anything else you're doing in the TX and here's the receiver. What ends up happening is if let's say that's the bounds of my radios or whatever you call it. Here's my channel. That's my propagation medium, right? So here's what I'm worried about. What I'm worried about in this case is that the channel might have some distortion. I'm not going to say might. Will have distortion. Okay. We often model this distortion in two things. So first of all, we have an impulse response, HCFT. Okay. And HCFT attempts to models the propagation environment. Super important. Okay. So that's what electrical and computer engineers do, in particular communications engineers. We use mathematics, we use computer simulations. We use a lot of tools, right, in order to model the physical environment around us to have a better understanding of it. And then the unwanted stuff, we usually, here's the noise, right? Unwanted signal. So what I'm worried about right now, we'll get to noise soon, okay? But this thing, right? This thing here worries me. And why is that? Because that thing can potentially do a lot of stuff with respect to that ideal signal, right? So how so? So the ideal representation, okay, for a channel is this, the delta, right? Because what happens? So let's go back. If let's say the output here is S of t, the input to the receiver is R of t, right? What I would like is my box HC of t, bloop. My ideal scenario is I would love R of t to be equal to S of t, absolutely zero distortion. And how do I pull that off? I convolve it. Well, first of all, we have this, right? So we have that. So what's the identity? How do we get the input to be equal to the output? That's how, right? That's how. But if HC of t is not equal to this identity, we start getting distortions, right? This is actually very problematic. Like, so for instance, if I have something that looks like this, like for example, so a side or example, let's do example. If I have HC of t that looks something like this, let me do it better. So it doesn't go negative. Yeah, that's it. So suppose we have something like this over time, 0. So imagine convolving your S of t with this, right? So if you have something like this, what happens? Okay, so first of all, this guy here, more realistic, okay? But this is also sad because that also means distortion. And what happens if you convolve your S of t? Let's say your S of t is a beautiful polar waveform, right? 0 to TS, let's say amplitude A. Let's just look at one period, okay? One symbol period. What is going to be the result of that? Well, if memory serves, it's going to have some sort of smearing effect. Yeah, there we go. Let me redraw that. I hope people realize by this time I'm not a great artiste, right? So what this will do, there's a rise time, right? Transient response. So if you go to RC circuits, right, like resistors and capacitors from your circuits class, more or less the same sort of concept applies. The electricity goes through this filter, or you convolve it, so it has a rise time and it has a fall time, right? It has these transients. They don't look like rectangular pulses to me. So now your receiver has to interpret now this sort of spread. Now let's actually, now this actually gets worse. Okay, so let's say we go back to, what was it? Let's go back a couple of slides. Boop, boop. Yeah, here we go. 1001101. Okay, remember that. 1001101. All right. So this should look like the following. Correct? Each one of these is one bit period, sorry, a symbol period, which since it's a binary, it's one bit period. It's the one and the same. Each one of these is TS wide, right? This is what each S would be individually. Remember, we're going to linearly combine them after, okay? So just heads up. So each one of these is that time segment of that bit. Now, when we pass it through HC of T, what do we get? Correct? Yes. Yes. We get these things. They don't look like rectangular pulses. You might say, oh, so what? Well, I'll show you. Ha. So what this is going to look like, so superimpose, add, superimpose. So what do we get? What is it again? 1 0 0 1 1 0 1. Let's draw the boundaries. And remember, this is with respect to time. And it will look like this. Mm-hmm. Yep. Yep. Again, not a great artist. So now, add them. Add. So very important observation. It doesn't stop at TS. Look at that. Look at that tail. Look at that tail. Tail, tail, tail. This is a problem because what this does is part of that symbol is spilling over into the next. That is ISI, intersymbol interference. My symbol is interfering with the next symbol and the next symbol. If that channel response, HC of T, is very lengthy, what ends up happening is it could even spill over into the symbol after the next, right? So like, look at it. Let's physically go back a couple. Yeah, here. So here I'm making the assumption, this is like, I don't know, TC long, right? And I'm making the assumption that TC is less than TS. But if TC, if this non-zero part of this channel impulse response is longer than TS, it'll spill over into the next symbol after next. I know, right? So what ends up happening if you add them together? See, now I'm. Let's really see my artistic ability. You're going to get something that looks like this. It's going to look like this, this, this. Even though my boundaries are here. Again, not the best drawing, but this is an issue. This is highlighting issues. Where do you sample to say, oh, that's an A, that's a minus A, that's an A minus A minus A, right? Right? So this I have to emphasize, right? So here, plus A, I don't know. Minus A, I don't know. So this is where we come in, right? And this is actually the subject of also lecture 9, very importantly, where we design some of these things. Okay, so let's go back to the slides. Right. So what we do as engineers, okay, is we have to counteract the impact of the channel filter. Right. So what we do is we try this. We create something called the transmit filter. Right. And there's a receive filter. Let's draw this out. So the way this would work is TX, okay, cool beans. Somewhere in TX, we're going to have this guy, right? That's going to be the shape. I'm going to pull that out of the TX. So everything else here is the bits mapped to amplitude values, yada, yada, yada. So this here could be things like that impulse train with, so W / is with the amplitude values determined from the binary patterns. Amplitudes, AI, okay? So this here is going to be the resulting line code or PAM or whatever you want to call it, right? Channel, okay? And then receiver, RX. So what happens is two things. Suppose you're an engineer, you're working on a project. This you have no access to. You can't change anything here. And same thing here, no access. Here, you can't control the environment. You just can't raise your hands and say, woo, and you don't have any more like distortion, right? So no access. Safe assumption. You can't move walls. Well, you could, very expensive solution, right? So what you do, no. So this here, channel, this is your overall transmitter, right? That's your receiver. So this is all that transmit machinery up to the whatever pulse. So this actually in past lectures we called F of t, right? When we talked about line coding, this was the F of t, okay? But here, because I'm inconsistent, it's H of t. So remember, F of t, H of t, right? Now, what you do is you insert something called H of t and H of R of t. We call this your transmit filter, okay, and your receive filter. These you have complete control over, okay? So the goal is how does this look like? So if I were to look at a signal here and here, so let's say that's my input to this cascade and that's my output. What does this thing look like? What's my my input to output relationship? If I were to describe this whole thing as one system. So I'm going to call it HE of t is equal to my pulse shape convolved with HT of t convolved with the channel filter HC of t convolved with HR of t, my receive filter. Okay, cool beans. So ultimately what I would like to do okay. So this here is some sort of equivalent, okay, impulse response. I can, like this here, what I would like to do, so this is the tool, right? So again, let's recall, I have no control over this. I have no control over this. Suppose I have a target equivalent impulse response. Therefore, what I do is I design this and this in order to achieve HE of t. That is what we do. Ha! So if I have some really bad thing happening in the channel, I have a rectangular pulse shape, right? What I would, and suppose I have a target, HE of t, what I would like to do is I would like to ultimately create an HT of t, an HR of t to convolve with what I cannot control to yield HE of t. All right? So that's the goal. So there's a number of ways of doing that, right? Let me rewrite it here. Mu. Yeah. Yep. HT of t, HC of t. So for instance, suppose I want HE of t to be equal to that rectangular impulse response H of t. Even though I said rectangular impulse responses are not really cool, but or whatever. Let's say this and this, I want them to be the same. So what must this thing, all three, boop, 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 got to be equal to? Delta, right? So what I would need to do is, in this case, something like HT of t convolved with HR of t needs to somehow be, okay, this must be some sort of inverse, must invert HC of t, okay? So there is something out there called equalization. And this is what exactly it does. What equalization does is it reverses the impact of the channel to create something close to ideal. You might not get a delta, okay? Like just FYI, you might not get a delta. In reality, your result of the equalization, you might get some sort of constant, and your delta might be shifted by some amount, okay? It is what it is. But you still don't get all that like awful distortion. You still get a delta, might be time shifted. So what it will look like, this response, when you equalize that channel, let's say that's 0, that's T naught, and this might be, instead of amplitude 1, might be amplitude C. I'll take it, okay? So that's what, like what you would do with T of t and HR of t, right? So that's how you would employ it here in order to reach some sort of H equivalent. Let's say in this case, I'm saying H equivalent's got to be equal to H of t. That's my choice. Let's say that's a spec that I'm given. All right. So that would be kind of the cascade here. Now, oh, yes. There's also, what is the frequency equivalent of this, folks? The frequency equivalent would be something like the following. So remember, so HE of t equals H of t convolved with HT of t convolved with HC of t convolved with HR of t. If I want to make the Fourier equivalent, so what is convolution in the time domain? It is multiplication in the frequency domain. So what I do is this now becomes HE of f is equal to H of f multiplied with HT of f multiplied with HC of f multiplied with HR of f. To me, that looks a lot easier to pull off, okay? Just between you and me, I would much prefer to do a product of a lot of frequency responses rather than the convolution of a bunch of time responses, okay? So, so that's super important because this allows us to more quickly realize implementations that otherwise would be very challenging. But heads up, if this fella was a rectangular response, this is going to be that very annoying sync response, right? Okay, so very important. And so, but nevertheless, something to keep in mind when we are actually building these things. So, okay, model again. So this is just going through again, sort of like the detailed mathematics of exactly what would be how we would work this out. So let's say our input response. So here's the pulse shaping I was talking about. So there's your H, and in the end, this here. This thing here is, so A of n would essentially, let's do this. I want to go back to the framework that I was just describing. So remember I have that transmit thingy, TX block. That's going to be equal to the summation, right? The summation AN delta TNTS, correct? And it goes into this H of t, and we get now this. And all of that is convolved against that waveform. So that okay, is equation 1. I just went backwards. All right? Now, the out, okay, ultimately is going to be this. Yikes. So forgot the E here. Okay, so typo, this should be HE of t. Okay? So then that equivalent is going to be all those. Oh, yes. So when we do that, right? So then we have this dupe. Then we have this H of t dupe. Then we have this HR of t dupe. What is that at the output? Well, WO of t, W out of t, whatever you want to call it, because here I'm going to call that W in of t. W out of t is going to be equal to AN of t delta t minus NTS. So that, remember, what does this look like? T, and that's going to be A1, A2, A3, A4, A5, A6, so on and so forth. This is my impulse train with the amplitude values per delta every TS seconds. And then that gets flushed through all of these. So that's going to be equal to, because that is that. Yeah, right? Right? So, got that. Frequency response. Boop. And now, folks, right? So remember, sync function, and we can manipulate this. So remember your signals and systems, your continuous time signals and systems. That's where 6 and 7 come from. Okay, so what I want to do is I want to come up with an example. Like the textbook, they did one thing, and I'm like saying, you know, they did one example. I'm going to go in a little bit more detail what's behind that example. Again, so there weren't like, and if you look at like the solved problems, sorry, the practice problems, like at the end of the chapter and stuff, nothing really digs into how this works and such. So I'm going to go into a little bit of this, okay? So let's go. So what I'm going to do is let's get into the weeds. Okay, so mu. Yes, here we go. So this is example. Schnikes. And of course, I have to scroll. Oh, one crazy thing as an aside. I want to bring this up. Remember that eye diagram thingy I was talking about? Very important, right? So remember this thing here? Remember what I was talking about before? So if you had rectangular pulses, so this is the reason I am emphasizing rectangular pulses a lot, right? So that's a great tool for identifying ISI. So, you know, if we had rectangular pulses, let me try this again. So as an aside, remember this. So with rectangular pulses, we got, let me try one more time. Boop. There we go. I'm going to put it here as an aside. Eye diagrams. How does this work? So ideal, what does your eye look like? It's going to look like this. 0, TS, right? And if it's a rectangular pulse and it's polar, it's going to look like either rectangular up to plus A, or it's going to rectangular down to minus A, right? Boring. And you're like wondering, like, why are we doing this, professor? But what happens if you have ISI? This is what happens when you have ISI. So remember, every period, whatever is in every period gets plotted. So what you're going to get is something that looks like this. And this is going to be my best attempt. So you're going to get transient, right? And then this is the point where the transient begins to go, oh no! What happens is transient. You're going to get that from the previous symbol dumped into that. Transient, right? And then you're going to get transient. So what you're going to get is like this garbage that's going to be flowing into your eye diagram. It's again, this is probably not the best representation, but what ends up happening is your eye begins to not look as ideal as this. So I would recommend, like, and we're going to do this in one of the next project. Should be square, but instead what happens is it looks rounded, and again, everything gets superimposed, right? So what ends up happening is your eye begins to close, right? And that's usually a good observation when you see your eye diagram. First of all, everything gets shifted if there's any sort of time shifting, and your eye diagram no longer looks like a perfectly open eye, or even if it's slightly closed, begins looking very messy because of these contributions from previous symbols, right? All righty. So now, so what we're going to do is let's look at, I'm going to go in a little bit more detail from your textbook, you know, Cooch 8th edition, example 313 from Cooch. 8th ed. Let me try that a little bit more. And so what they talk about is you have unipolar. We know how that looks like. Non-return to 0. So if I have 1, 0, 0, 1, it's going to look like this. Boop, 0, 0, 1, right? 0, TS, 2 TS, 3 TS, 4 TS. Okay, great. Awesome. And what happens is my filter, my channel is an RC low pass filter, RC LPF, right? And they recommend, okay, they recommend checking out, okay. So the equations you want to look at, check out equations 2.145, 2-146, and 2-147. Okay. So what this is going to look like, okay, this is very important. This looks pretty much like what the distortion that I've been talking about. What that HRC, which is the channel environment, is going to look like this. Whoa. And it's going to have amplitude distortion. It's going to scale it down by RC. And my time constant is going to be equal to that guy, 0.37 over RC, right? Very importantly, what does this look like in the frequency domain? The frequency domain, this thing looks like this. So let's look at the power spectral density. It's going to look like that. What's the height? 1. And at the 0.5 mark, this is my 3 dB bandwidth. 3 dB, because I'm 50% of the way down from the maximum, right? That's going to be equal to F naught, 1 over 2 pi RC. Okay, great. Mathematically, how does this look like? Mathematically, HRC of T is going to be equal to the time constant, right? E to the minus T over T naught. So it has some sort of exponential decay. And that's for T that is positive values, and it's 0 for negative values. Okay, cool beans. Frequency representation, it's complex. It's going to be equal to 1 over 1 plus J 2 pi RC of F. And the power spectral density, magnitude squared, mu is 1 over F naught, where F naught is equal to 1 over 2 pi RC. Okay, awesome. So we're cooking with gas here. So now, what's the next step? Well, I want the frequency representation of that unipolar thingy, right? So mu. So this guy, unipolar of T, right? What is that going to be equal to? Well, by definition, that's T minus TB over 2 over TB, right? And TB, TS, remember, TB in the binary world, right, is equal to TS, 1 bit per symbol. So just heads up. Now, frequency representation, unipolar, non-return to 0. Non-return to 0. F, okay, what is that going to be equal to? And this is where, yes, thank goodness. TB, sine, it's a sinc function, pi F TB, pi F TB. But wait, heads up, I got a time shift. So what this has to be equal to is e to the minus j 2 pi, right? TB over 2 F, right? So we got that. So now what happens is from this, what do we have? So what we get is so far these two things. If we were to get HE of F, what we're going to have to do is we have this fella, okay, multiplied. Remember, in frequency, it's multiplied. HRC, that represents our channel. Okay, now, so this is going to be equal to TB sine okay, and then E over 2. The 2's cancel out, okay? So I should have done it sooner. And then boop, boop, those cancel out as well. Now, what's the RC? 1 over 1 plus J 2 pi. I forgot, so I have to go back. RC, okay. RC of F. And again, shorthand here, I could just do F over F naught, right? So I could just do that. So now I have that, plus don't forget, now I have to do the transmit filter and the receive filter. So, so a possible question would be, how do I design this thing, right? How do I design this thing such that I get unipolar, non-return to zero pulse shape at the output, right? And the answer is I would need sort of the naive answer is this would have to be 1 plus J F over F naught, naive. And so we would need to split this up, right? So this would be the frequency response of these two together in order for, suppose the target is this. Right? So I would need to nullify somehow the impact of HRC, right? So that's how I would have to do this, right? So that's how, and what some folks do, right? With equalization. So there's two ways to take care of it. So there's equalization. And so what equalization means is I don't do anything at HT of F. I just let it be equal to 1. And I do everything at the receiver, right? So whatever signal comes in, so all the heavy lifting's at the receive filter. There's also something called pre-equalization, where I do everything at the transmitter and nothing at the receiver. Pre-equalization. So everything is there. And nothing at the receiver. It's just unity. There are pros and cons for each. Equalization, it's great. Essentially at the receiver, if I know what the channel conditions are, I can tune F naught, because let's say F naught changes. Let's say the resistance and the capacitance changes over time. That's a problem. But the problem is if I have noise, we didn't talk about that. I also apply my filtering to the noise, and there's some reasons why I don't want to touch the noise at the receiving end, because there's potential for me to amplify the noise, right? Because everything that comes in, it's whatever signal plus noise. So ideally, I don't want to touch the noise. Pre-equalization, I do everything beforehand. I pre-distort my signal before it goes out and hits the channel, the HC of T. And that's great, because what ends up happening is the output of all of that, right? The output of the distortion will be the ideal signal, the HE of T that I want. And then I add noise and I don't manipulate it. But the problem there is the receiver has to send to the transmitter, hey, this is your channel environment. Not ideal either. So both have their pros and cons. All right. So lessons learned from this lecture. So we looked at this idea of, first of all, rectangular pulse shapes, not so good in terms of bandwidth, right? Spectrally just like sprawls from -infinity to infinity. We looked at this concept of the equivalent filter and how we have transmit filters and receive filters, and how we do equalization. Very importantly, also, we looked at the concept of the channel and ISI, this smearing impact, and how it makes lives harder, right? So, and we quickly went over example 3-13, right, 313. And we actually put in a channel, a realistic channel that could cause problems to us with our communication system. And so this example I went through, you should study it. You should see, where did Wyglinski come up with all these things, right? So with that, shucks. Let's see if there's any other lecture slides. Nope, that's it. So with that, that concludes lecture 8 of ECE 3311.